done it. We've transcribed and we've translated. So on your worksheet right now, you have multiple strands of DNA, and there's a blank on the DNA. This worksheet is different because it gives you the strand of mRNA, so you have to work backwards. All right? Then it's asking you to code for the amino acid, and that's when you use your little table. So just to get started, because this part is part of your lab, I want us to figure out what the DNA is. So we're just concentrating on that first line. Before we do that, let's just have a review. If you have DNA and you're transcribing it, all right, to another strand of DNA, so you're going from DNA to DNA, what would be my complement strand? What do you think? And I'm looking at the ACGTAT. So I want my complement strand of this. So that means, and it's DNA to DNA. What pairs up with these letters?
T.
T goes to A goes to T, C goes to G.
T, A.
All right, Romero, I'm going to have you answer. Start with A.
It'll be T.
Very good. Christina, C.
G.
Very good. Diane, G.
C.
Sable, T. Ian, A.
T.
And Jeremy, T.
A.
Very good. All right, that's DNA to DNA. All right, that's called transcription. But now we want to go to translation, which means we're sending it, we're changing it, transcribing it to messenger RNA. There's a change. There's one change.
A goes to U.
A goes to you. Very good.
So that
So
means U goes to A. Base.
A goes to you. A goes to you. T goes to what? Very good. C goes to what?
G.
Very good. G goes to?
G.
And T goes to?
A.
Very good. So this is your mRNA strand. How many of these code for one amino acid?
Three.
Three, very good. So 3. So here you have ACG, and here you have UAU. This is when you would use your table and you would find out what 3 letters code for a protein. All right? Very easy. The only thing I'm asking you to do is a review. They gave you mRNA. You have to work backwards. All right? So let me ask you this. Are there ever any U's in DNA?
No.
Never. So now all you're going to do is you're going to work backwards. All right? So looking at your strand there, find the DNA by working backwards. So whenever you see an A on the RNA, what should you see on the DNA?
A. T.
T. Very good. T. All right, so just work backwards. I just want you to do the first strand.
What's T on it?
It's transfer RNA. All right? And so for your purposes, we're just going to stick to mRNA for right now. All right? So just do the first strand and work backwards. I just want to make sure you guys understand how to do this before we go on to enzymes, because enzymes are related to the way the DNA codes, and we're going to learn that. And I'm going to ask, I'm going to call on you guys to make sure you understand how to do this. So, tell me when you're done. Raise your hand or put your pencil down. Good. That quick?
Yeah.
Wow, that's great.
Yeah, I'm not making up already.
You got it? You got this. You know it. Okay, Ian, you done? You guys done? I know you did. I told you that. Only you 2 did them. Maggie, you're done? Boys, you're done? Good. Sable, you're done? Trey, you're working?
Yeah.
Okay. So we're only reading number 1, the DNA. And I just, again, want to emphasize the importance of how those complements line up. If something doesn't line up, it's not going to code for the right protein, or in this case, we're going to be talking about enzymes today. Ready?
Yeah.
All right, Trey. Is it okay if I pick on you?
Yeah.
Give me your strand. From RNA going to DNA. All right, follow along. Make sure you got the same thing.
So start with the DNA.
Yep, tell me what you wrote for the DNA.
T A C T G A T C G A C C C C C A T A T G A T C.
Everyone get that?
Yes.
Okay, so we got this. It's pretty easy. All right, so put that aside for now. Now, focus on the PowerPoint on enzymes. This is new. How many of you guys have ever talked about enzymes before? You guys even heard them, really understand them?
Enzymes, yeah.
They're a little complicated. So I'm going to go through the PowerPoint, going to emphasize some things, going to show you a 3D model of an enzyme. Before you leave today, you got to make an enzyme for me. You can do it at the beginning of the period, you can do it at the end. I don't even care when. You just gotta show me you know what you're doing. And you get to play with Legos. So that's the fun thing, right? You're gonna use Legos to make this enzyme. I was trying to do it this morning. It's a little bit more challenging than I was ready for this morning. Sam Lameth is the one who like, boom, got this together, actually. So you guys are probably a lot better at it than I am. All right, so let me just go over enzymes real quick. I'm gonna leave that on, I guess.
Where do I spring go?
And then we're going to go on, and you guys will have time to work on your own. All right, so enzymes, I want you to pay attention. They're proteins. We figure out proteins by coding DNA. They're catalysts. They speed up a reaction. Nope, not right now. And they're affected by temperature and pH, and I'm going to show you a little demonstration. All right, the first thing, what are they? Only write what I tell you. And you can even use it, you can write in bullet form. Enzymes are is what you're going to write. Well, what are they? I already told you they're proteins. You can just use, again, bullets, just like I did. Enzymes are proteins. And they're 3D.
Okay.
That's all you need to know right now. So you're going to write what this says. They're catalysts. That means they speed up a reaction. In number 3, up there it says they're not changed by the process. Here I said they're affected by temperature and pH. So those 3 things are really important to know. All right. So enzymes are proteins, and they're in yellow up there. They're proteins. They're catalysts. That means they speed up a reaction. They're not permanently changed in the process. And they're affected by temperature and pH. Enzymes control so many of the processes in living things. That's why they're so important, and that's why we use them in this lab, again, as a comparison. All right? Tell me if I can move on. Nope.
Oh, yeah, it's, yeah.
Now, in a minute, I'm going to actually give you the information on the PowerPoint. But this is an enzyme. It's 3D, all right? They're specific to the reaction that they work on. So all of our enzymes, all the different enzymes in our body have different shapes. This one's just an example. They need something to work on, all right? They have to be a lock and key. This is what it works on. The enzyme is right here. This is the active site, the part almost that sort of interacts with the substrate. It comes in. Oops, wrong way. It fits perfectly together. That's what an enzyme does. It's a lock and key model. Has to fit together. It's shape specific, otherwise it won't work. But look what happens if something comes and mimics, imitates. It's the same shape. All right? That the right piece is. Let's look at this piece. What happens if this piece, it's missing this little chunk, but the base is the same? What happens if this one comes in and goes right in here? Do you think that enzyme's going to work?
No.
Why?
Because it doesn't have all the, it's
It
missing.
didn't have all the parts. It sort of fit in there, but it's missing these 2 key component parts. So it's not going to work real well. So it has to be the exact same shape. Now what if, though, I had this part? My enzyme's falling apart. What if I had this part? I'm going to put it in here. Do you think that one's going to work?
No, too much. Too much on
It
one.
comes off. Actually, though, because that active site is activated, it might work a little bit, but it's not going to be real
It's
effective.
not going
Plus,
to function the way it's supposed to.
exactly, remember? And this part's off.
Mhm.
So when I told you guys have to make your enzyme today, I don't care what you do. I don't care what shape you make. You got to show me your enzyme so that I know you understand this shape thing is so important. And you got to make your substrate. It can be as big or as little as you want. You can do it right after the lecture or right before you leave. It doesn't matter to me. I just want to know that you understand this lock and key model because it's really important. All right, so that's the first part. Okay, let's go on to the second part. There it is. It's 3D in our body. It's globular. They are reusable. All right, so there's, again, my enzyme I was showing you. this is my enzyme. This part is the active site. It's right here. And this little part is the substrate. It's called the substrate. It's the part that fits in there that it recognizes. All enzymes, so I want you to write this, are reusable and they end in A-S-E. So that's your next bullet. Enzymes are reusable. You can use them again and again and again and again. And they end in A-S-E. And they usually, that's funny, my daughter's very good at that, I'm horrible. They usually work on the molecule that sounds like them. So, for example, sucrase is an enzyme that works on sucrose. Lactase works on lactose. Maltase works on, very good. Now, let's talk about lactase for a little bit. Does that sound familiar to you at all?
Lactose intolerant.
Very good. Tell me what it means now. You know what lactase is? Tell me what it means.
Your body doesn't work good with milk.
Or anything dairy.
Very good. Now talking about enzymes. What are you lacking maybe if your body doesn't react well to it?
Lactase.
Very good. Why are you lacking lactase? What makes it? What were we talking about?
DNA.
DNA. So if something's happened, you don't have the right code to make the right amino acid to break down lactose, you're going to be lactose intolerant. Very good.
So when like your DNA is not right, that's what can cause like allergies
Sucrose is a sugar.
Absolutely.
and stuff.
Yeah.
Maltase.
What's that?
What's maltase?
Maltase, it will work on a sugar called maltose.
Molasses.
Alright, let's move on. Okay, don't write anything down because it's a little complicated. I told you that enzymes speed things up. A reaction may still occur, but an enzyme makes it go faster. Alright? And the way that it does it is it just reduces or it lowers the amount of energy. If we relate it to how big a hill is, it makes the hill smaller so the reaction can go faster. Alright? And that's what it means. Enzymes work by weakening the bonds, which lower activation energy. And there it is. The pink one shows you what happens when you have an enzyme. It can go faster because the hill isn't as great, so you don't have as much energy required. And the blue one is without the enzyme. Alright. So now I'm going to show you something. There's the enzyme, the Lego piece. There's your substrate. That little piece in there has to be okay. It's got to be all right. Can't be broken, can't be chipped, can't be modified, otherwise it's not going to work. So there we go again. There's the active site. The substrate's going to fit right in there. A change in the shape of an enzyme's active site induced by the substrate. Sometimes you'll have that and then the little substrate breaks apart. That's what we want to happen. Okay, so I want to show you something now. I'm going to tell you potatoes have this crazy enzyme called catalase. I did it for you this morning. I'm going to do it again. All right. This is raw potato. You can also find catalase in liver. Yeah, I hate liver.
Yeah,
All right.
right. I'm happy to do with potatoes.
Now I did this morning, and I'm showing you this because when you do this enzyme reaction up here for biodiversity, you get bubbles. You get a fizzing. That means the enzyme's present. It's fizzing. So I put these potatoes in just hydrogen peroxide. And very quickly, look at the amount of bubbles that it formed. All right? Now, I didn't try the one that's cooked potato. Do you think the cooked potato is going to have the enzyme catalase?
No, because it's probably boiled out of it.
Very good. So we're going to try it right now. I haven't done it before. So, I'm going to try it right in front of you. We're going to see if there's a considerable difference. All right? So there's all that bubble stuff. It hasn't gone anywhere. That's because it produces oxygen gas. All right, so there we go. So here it is. And if there's time, you guys can do your own experiment later where I give you different things and you can tell whether or not it has catalase in it. All right, so there's my little potato. All right, so I'm going to have you hold that in. Got to get my hydrogen peroxide back here. All right. And remember, why don't you bring that crushed cooked potato up? I'm going to have you hold this one. Christina, is that all right? So, that one's raw potato. This one's cooked. In sandwich She mashed it all up for me. Look at that's baked potato from this morning. I could have eaten that for breakfast. All right. Now, again, that one's cooked. So we're gonna assume that it doesn't have that enzyme in it. I should probably try and put the same amount in each, right? Why is that important?
Because you wait.
Reducing any,
Yeah,
You could get most of those.
exactly. Do I have more in? Okay, so here we go. This one's the cooked one. Hold that one.
There still might be bubbles, but
There's-
it's not gonna be
Right, so
as
we'll see.
much as the one that's not cooked.
All right, what do you see, Ian? Are there bubbles starting?
Yeah.
Any bubbles in yours? Little bit? All right, we're gonna leave them alone. You can already see though, that the one that's not cooked, look at the amount of bubbles that are like going up. It's pretty
And
crazy.
you have more, cooked potatoes in than you have.
I do. That's a good,
Yeah.
you know, when you're on, you astound me. You
I know, I
really
found
do.
myself.
I know you do. You really do. When you're on, you're like, ah, I love it.
it's almost like electroplating
You
metal.
see how different that is?
Yeah.
All right. There you go. You see it? Good. All right. You already noticed this. And the bubbles are already forming.
Yeah.
Okay. All right. So I'm going to leave that up here. Okay. So why is the fizzing important? When you do this experiment up here, you're either going to see fizzing or no fizzing. What does fizzing tell you? The enzyme is in there, which is a protein. Very good. And that's how you decide whether to eat or not to eat. Okay. There we go. One more
Wouldn't it
thing.
mean that's in most of the sodas, because most of the sodas fizz up?
What's that, honey?
Wouldn't it be in like sodas as well, because sodas
No,
fizz up?
that's, carbon dioxide. It's
That's
been pumped in at high
good
pressure,
point.
so it actually combines with
Very
water.
good point. Bubbles can come from carbon dioxide too.
Right.
All right, okay. Next one, we're almost done. Stay with me. All right. Now, what affects activity? And then I can just write this down, it's very important. Environmental conditions. Oh, well, I wrote it up there already. What environmental conditions are going to affect an enzyme?
Temperature,
Temperature.
pH level,
pH, which means acidity. All right. And enzyme inhibitors. Oh, what does that mean? Okay. An enzyme inhibitor.
something that blocks it from working.
There you
Yeah.
go. An enzyme inhibitor might be another molecule that comes in here and blocks the site so that the substrate that it's supposed to act on can't get in. It blocks it. It inhibits the reaction to occur. All right, so that's what that is. Now, what would your guess be? Is temperature, increased temperature, going to speed up the reaction, or is it going to slow it down?
Speed it up. Yeah.
Speed it up. What about decreased temperatures? Slow it down. What about really, really, really hot temperatures?
Speed it up.
No, speed it up because it's just ingredients. It just increases reaction.
So let's say this is a real enzyme. What is really, 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 really hot temperatures? If I put this in a fire, going to do to this?
It's gonna kill it.
Yeah.
Specifically, what is it going to do to this plastic?
Melted.
It's going to melt it.
Well,
And if it melts it, this actually happens in your body.
It's
Is
not
it
in
literally-
the natural structure anymore. It's been broken down.
Very good, and it's called denature. I'll write that down, and we talked about it on the slideshow. This is why when you have a really high temperature in your body, you have a fever, it affects all your metabolic processes. You're sick because the enzymes can't work the way that they're supposed to. All right, so if you've ever wondered, who cares about a fever? Sometimes I have a fever, but I still feel okay. It's blocking this metabolic activity. That's a dangerous thing. Because literally, it's the way if I threw this in the fire, it's gonna melt, it's gonna get all sort of disfigured, that substrate can't come in here. That's what happens in your body, the reactions aren't gonna occur. All right, so there's a perfect optimal temperature for all of your metabolic activities to happen in your body. What is that perfect optimal temperature?
98.6.
98.6, there you go. That's the temperature that our body likes for enzymes to work. Different organisms have different optimal temperatures. Different enzymes work better in optimal temperatures. All right, one more thing, and then you can either play with the enzymes and make them from the get-go, or you can do it towards the end of the temps are going to unfold it, denature it. pH, we like around 6 or 8 in our body. That's about neutral, 7. If we start getting very acidic, disease, chemicals can occur that we take and do that, then it's not going to work the way that it's supposed to. All right, we talked about that a little. That's just an inhibitor. Something comes in the right shape, and it won't let the substrate in. All right? Same thing that we were talking about before. Okay, so this is what I want you to do. I'm going to repeat. By the end of the period, I want you to make an enzyme. You can work with someone else. You can work alone. All of the Legos to make your enzyme are right in here. I'm gonna be honest. Some of the parts don't fit well together because this is just sort of a combination of Legos, right? I don't know how many of you guys liked Legos when you were kids.
I love Legos.
Do you like Legos? My daughter, female, right? Loved to build. She's still sort of crazy about puzzles and things fitting together. These are all her Legos. She has Legos, she has big Legos, small Legos, Lincoln Logs, and love to build. Great. You get to do that. It doesn't have to be anything fancy. You just have to be able to prove to me that you understand enzyme. You got to show me the active site, substrate, how they fit together. That's all you have to do. Time by the end of the period.
You don't need a base, right?
What's that?
You don't need a base.
Nope. All you need is something that fits together. All right. As long as I know you understand. The second thing I want you to do, you now have the time to go back to your lab now and understand this enzyme. Lab, right? That's the part. It's going to say fizz or no fizz. That's all you have to do. And another type of enzyme that you use is called a restriction enzyme. Your scissors in this lab, when you're doing your DNA gel electrophoresis, act as the restriction enzyme. All right? That's a little bit different than what I was talking about right now, but still an enzyme. So those are the two places that you see it. Now I feel like you get it. Why are they so important? Because enzymes are proteins. How is that related to DNA? DNA codes for proteins. Your DNA, like you said before, is askew. Something's off. Doesn't mean you're going to die or anything, but you might not have the right code to make a particular enzyme that's breaking down something in your body. You're missing it, or it's not working quite right. That's why you can take lactate if you're lactose intolerant. You can take this little tablet called lactate, and it helps you digest and break down the lactose in your diet so that you don't just have to avoid it altogether. All right? Do you guys have any questions? You feel like you get that?
Yeah.
All right? Okay. So, I will give you your labs back because I have them all. And then you can start on your lab. And I'm going to come around and help you out if you need it. And if not, then you don't. Okay. I do have all your lab minutes calculated. So Jeremy, here's yours. All of them are calculated. And we can talk about that over the next 20 minutes if you want. If you have questions about, how am I doing?
Can I start the advertising?
Yeah, you can start. You can do that. Oh, Joe Klein's out here. Okay, Sable. You're doing so well. Ian. Craig. Jake.
He's been testing.
Does everyone have one? Diane? And Romero, you started yours. And Christina. Yours is the last one. There you go. Pencil. Use a pencil. Anyone? I would prefer that you do it in pencil. And I'll come around and make sure that you're okay, that you know what you're doing. Trey, you did like Legos, didn't you?
Yeah.
I can tell. You have like an affinity for those. All right. You girls know what you're doing and feel good about it. The table to code for this is back behind
I
you.
have literally nothing on it.
Okay?
There's nothing.
You doing okay?
Recently, every day.
I will sit down and help you because you were gone. Maggie, you're good. Here. Sable, you're good. I know you are. I believe that your current photographer is sitting up there. All right. I just don't know which one it is. I think your name's on it. It's right there in the corner. You know what you're doing now. How are you? Feel like you got it? Is there any help that you need, or you got it? All right. So Romero, I'm going to work with you. Okay. pencils, somewhere, yep, there you go. Late, but man, we're coming late. Basically what this lab is, it's trying to get you to understand biodiversity and why plants are really important. And if you read the lab, it'll tell you that this one is needed. What does that mean? Yeah, it's gonna be extinct. The reason this is so important is because it makes us a cancer curing agent, right? We're trying to figure out which ones are like this, medicinal. That way maybe we can take that cure all out of it. So, this is your whole observation sheet. This is where we're going to collect and record all your evidence. We're going to draw it here, the pictures of each of them. We're going to look at the seeds and draw them, and look at the stem structure. Hey, Sable, would it be okay if I just borrow your lab for just a sec, honey? Thanks. Only so I can drag on it a little bit.
Ask Miss Blue.
It's fine, come on.
Yeah, come on.
Those are all.
He said,
Oh my god.
Okay.
Yeah, so those are the first three. Pretty easy.
This is someone's picture, but you know what I'm doing.
Is that station up there? The only difference is the extracts are up there. That's another part. Alright. The next is the test for menthol. That's so easy. You get those little templates up there. You put a little bit of alcohol and mix it with your extract and you write on your list. And you're trying to see which one has the most. Alright. Which one is, again, most likely to cure. Final one is the DNA. You were doing up there coding. Now, without you looking at all of this stuff, what is the best way to code for these? You and I look alike, or we like? What's the best thing? I want to know if you're my brother, you're my son.
DNA?
That's absolutely colossal. That's like the nail in the coffin. And their DNA is the same. DNA absolutely the best way. So, when you do all of this, all those other things are not really so that DNA is like, but, so, and I'll read you this. I'll show you how to do very self-explanatory. So tell me where you want to start and I'll put it on. Okay, yeah, let's go do that. All right. Very good, honey. Thank you so much. Okay. Do you remember how to do it?
A little bit.
Not that big. It's a technique used to separate plastic.
Oh, yeah, I know this. Separate color.
Yeah. So, do you want to do that on your own, or do you need to set it up? Okay. I'll be right there, honey. I appreciate it. So, usually happens after a while is because you cannot have this water line higher than those soft so they can get to to know that when the water comes at the top, take it out.
I don't even know what the hell I'm doing for this. I was just told look for all the things where you see CC and GG next to each other and then cut between them.
You do whichever one, which one? Well, this is the difference in amino acid sequence. I think what I saw you do is you already completed it. Already, right? This is how you report this is called tonic curves. You're comparing the tonic curves to each curve, and you're telling me which one is right. So let's look at this. Let's do twins. Just look at their protein. How many do they have in common? Just look at the bottom three. How many proteins do they have in common? One, two, that are the same? Is this the same right here? Did you compare this to?
Yeah, bro.
Is this the same?
L-E-U.
What is that? Okay, I'm sorry. This can't. So three, is this the same?
No.
So five? So on your data sheet, you write, the tonic cures you can't. So tonic cures and X, you're going to say 5 proteins in common. Does that make sense? Now you're going to compare the tonic cures and
Should I write 5 in here?
No, honey, because this is comparing it to itself. Anybody has this? Oh, you just switched the five. Okay. So then that's all you do now. Now, this is confused, so write this on here. This one, this, you're only doing the tonic cures and that's the tonic cures. Somehow, when you write that little one and the last one, you don't read anything but comparing this one and this one straight down. Okay, so you write that, and then you're going to hide open, and I'm just doing that so that you know. So, Mary, did you get that? You can leave that alone, honey, because it's gonna take a minute and you'll put over here.
I'm just gonna cut and take things right.
And then put it in the proper row. Here's your little thing. Here's your indicator table. So what I would do is just invite. You can do whatever you want.
I'm already figuring out.
I know, but I just trim them as thin as possible to make them better. Because then it creates. Was that 12? So change it right there. Where's your little logo for it?
Jeremy told me that I was supposed to cut in between the
Ray, you really like Legos. You really buy Legos. Okay, you know what you're doing? Yeah. listing which one has this enzyme in it. So you're gonna put 5 grams for each of the solutions, 5 of X and or BS, BC, there, so 5 of X in there. How are you gonna do it? Just show what you see. All right, you got scissors. So tell me what this part is.
This is the base site.
So what is it called? We have 2 words, enzyme and substrate.
Diane, art.
Very good. So on this one,
I gotta take it apart.
this one,
I was just talking to you,
right?
it's not my turn.
So I've been taking it apart with that.
Leave it out. Leave it out. Right there, you're right. Sorry, you're right. And you can say dark green and sugar. So does that make like sense to you?
Yeah.
Let's go to them.
I understand that.
Let's go to them.
Yeah, thank you. Okay, now, let's read the lab. Let's see what it's telling you. Well, there you go. So you are good. All right, so it says using simulated jump.
Yeah, 13, 13.
So these are your strands of DNA. Yeah, right? The first thing. Nope. We're not going to show this. Okay, remember I told you this one talks about enzymes. It talks about restriction enzymes. This represents a restriction enzyme. It's going to cut it. Where is it going to cut it? It tells you.
Oh,
It's like blocking heat. Every time you see the CCG combination, those 4 letters in that order, shade it. So start with the conifers. Get your pencil and shade every time you see CCGG shaded. Yeah. Oh, I like that one, Ed. Very nice. What is this called?
Base site right here,
This is the active site. Yes.
Yeah.
So what's the whole thing called?
Amazon,
Very good. What's this called?
subsidiary.
Substrate.
Yeah,
Very good. What are the 3 things that will affect that enzyme to work right?
pH, high temperature, and very low temperature.
Very low temperature. And pH, catalyst. And it's something that inhibits it. Yeah. So good. Good for you. Nice, nice, nice. I like that one. Put that one aside. Yeah. Yes. Just give me 1 minute. I just want to make sure that I explain this. Okay, so let's focus on this one. So then that way you don't have to do this. All right. It tells you after your breath. You guys are each site. It cuts it. The C and the G of those 4 letters. So it's going to cut it. So you're going to come and you're going to say, I'm the restriction enzyme. Cut.
I've done 3 of them.
Restriction enzyme. Cut.
Chromatography, enzyme test.
And restriction enzyme cuts. Now, this restriction enzyme cuts between the C and the G, but depending on what enzyme you have, it might cut somewhere else. Okay, then what you're going to do is you're going to cut off the label, and you're going to tape it. This is all important information here. You're going to take your data table. You're going to tape your botanic purist label right here. You're going to count the numbers of letters in each little piece, and you tape it to the number that it corresponds to. This one has 5. We're going to trim it, Christina, so that it fits in that little row. And you're going to tape it right there. And they're going to do the exact same thing with all of the pieces of DNA. Does that make sense? Yes? Good. This one has that.
Speak to what it says.
Yeah. Oh, look at that.
Yeah, I think it was a little bit, I was like, I'll be better.
And then trading makes the
Here's the indicator powder.
What?
Yeah.
It makes it.
Mine's perfect.
Yeah.
Alright, those are your 5 fingers.
Why was they taking the charge, Dave?
You can just use mine.
Why must they take the charge, Dave?
It works.
Take
Makes
that.
me angry.
Hey, Cheyenne. So I got Ed to show me his active site and his enzyme. I got Trey too. Ed, were you working with someone when you
No.
did it? Were you working with someone?
No.
All right.
Can I go to the bathroom?
Yeah, let me do that. I'll show you how to do that. So go to your observation at the end.